Earth Science Time. Today we are talking about, we're going to call this astronomy in general, and you are probably already aware, I hope you're already aware, that astronomy is kind of, in a way we use that word just to be the study of space, like space science. And we've been, I don't know if anyone saw that. I just made an actual three-pointer with my little piece of plastic I was throwing away. But astronomy is the study of space, and we've been doing space science for about a month already, but I specifically want this to be called astronomy as opposed to space science because the word astronomy actually means, you probably know what astro means. What is that? Star. And nomi, okay, star. Just don't, come on, Justice, pay less attention. Nomi, what?
Elliot.
No. Nope. Nomi. We're used to things like geology and hydrology and biology, which that means what? What's ology mean? Study of. We're not doing astrology because you know what that is. No. Try again. You know what's nomi might be?
Short little badge of funny hat.
No, it's related to, you won't be aware of this probably because some of you don't speak the French because you hate them, and others don't speak the French just because you haven't learned. But it comes from the Latin for to name. So like, I was going to say a nom de plume is French for a pen name. Like when someone writes a story under another name besides their own, that's called a nom de plume. Another thing is a nom de guerre, where a spy especially, will take on a name that isn't theirs to like disguise themselves. So nom, like Spanish nombre, right? You know that one probably. Name. And so they're related. So this is to name the stars, but really when we're talking about fields of research or fields of study, it kind of means we're going to also be talking about astrometrics, which is to measure the stars. I didn't even give you a chance to say what metric means because you should already know. I don't want you to embarrass yourself. You should already know that metros is from the Greek for to measure. That's why we get like meter or trigonometry and things like that. So, or geometry. So we're talking specifically about measurements about the stars. Measurements about the stars. And not just the stars themselves, but space, the entirety of the universe. What is the universe? What is the universe? Someone give me what they think is a good definition, please.
Everything.
Yep. Okay, I'll buy it. Everything. Well, if we were being scientific, we might qualify that to be that it includes everything that we can do what with in science.
Everything we can perceive.
Not just see. I know what you're getting at, but I want you to use, I like that better. Perceive is better. If we're perceiving something, but not only just glancing at it, not just noticing it, but kind of categorizing it, we might call that, instead of perception, observation. I don't hate comprehension, but I'm going to put observation. Everything observable. And this is extremely important to me, and maybe to you too, because there are schools of thought in which there are parts of the universe, maybe not parts, but facets of the universe that are unobservable. So remember, science, we talked about this at the beginning of the year, science is concerned entirely with observable phenomenon, things that we can see, hear, sometimes taste and smell, touch. That we can ourselves do that, or we can use instruments to help us do that, like telescopes or microscopes. Science is concerned entirely with those things. Now, if you ascribe to a school of thought where some things in the universe are not observable, which we won't get into that, but if you ascribe to that value, then maybe science deals with the observable universe. So everything observable is the scientific definition of the universe. And what does that include? Well, let's go down the scale. What large-scale things are in the universe? We're going down in scale, meaning, let's start with the top. So galaxies. There are larger than this. There are galaxy clusters. In fact, let's write that because I think that is one of the things that your book talks about. So there are galaxy clusters. You know what a cluster is. Let me think of how gross I can make it. If you've ever heard of, or maybe experienced a cluster wart, that's when there's lots of warts. I could have said grapes, but I chose warts. So a cluster of galaxies is a group of galaxies bound together probably by what, unlike warts? Gravity. Yep, good. Okay, and then within galaxy clusters we have galaxies. Which are a group of what? Bound together by what?
Planets.
Okay, two people said not necessarily the wrong answer, but not what I'm looking for. Yes, stars bound together by, again, gravity. Okay, and then galaxies are themselves comprised, as we said, of stars, but not just stars, star systems. Remember, one of the CCCs is systems and system models. Remind me what a system is.
A system is like a network.
Okay, I love that. A network with this hand gesture. I actually really like that because it's not, the common definition is a group of components working together, and I do not like the phrase working together because that implies agency, which we don't necessarily need to ascribe to them. Kind of like back to the observable. Maybe there's something unobservable where they do work together or want to do things, but in science, we don't observe them working together, we observe them being interconnected. So a web. So star systems are different components, not just stars, different components that are operating together. Okay, and that's again held together by gravity. Okay, and then star systems contain within them stars. List more. I'm going to put these on the same level. Planets. List more.
Solar system.
Well, that's a star system. It's just that ours is called the solar system because of our star Sol. Moons. Okay. List more. Asteroids. Kind of asteroids, right? Are there more stuff? Are there apples? At least in this solar system, there are apples because there are some on my countertop, and I live in this solar system. So there's more stuff. Obviously, this is not an exhaustive list of components, but these ones at least largely are held together by. So we could probably say, maybe even put that little bracket up to there. The fundamental underlying force that holds this all together into one is primarily gravity. Why? Why that one? Out of the four fundamental forces of the universe, why gravity?
Strongest.
Nope, absolutely false. I appreciate that you said that, and I'm not trying to be harsh. I wish I had said that differently. But it is the weakest of the fundamental forces, by far, by orders of magnitude, by 10 to the 15th, it's the weakest.
Not only are you wrong,
But let me say it this way. Not only are you wrong, but I'm so glad you said that because people often think that's true. What are the other four fundamental forces of the universe? Okay, electromagnetism. What else? You should remember these from physical science. The other two have the word nuclear in them. Do you remember?
nuclear fission.
That ain't one of them. Strong nuclear force, and the weak nuclear force. These are the four fundamental forces, and these ones are not what hold the universe together. The strong nuclear force holds atoms together, so in a sense that holds the universe together, but on a much, much, much smaller scale. Also the strongest. Electromagnetism, as you probably are aware, you should be aware because I've told you this many, many times, holds positive and negative charges together and repels negative and negative charges or positive and positive charges. And the weak nuclear force is kind of spooky, and it is the force that can transmute a proton in a nucleus into a neutron or a neutron in a nucleus into a proton. We're not really worried about that one today. We're not really worried about that one. We'll talk about this one later, but this is the one. I'm saying words like this, but gravity is the one, which reminds me I should switch. Is this going to tell me if this goes to picture-in-picture? Did it? Okay. Okay, so gravity is the one that holds these things together on the, not because it's the strongest, but on the largest scale. Exactly. Thank you, Ty. Because it acts over the greatest distances. So where the strong nuclear force is the strongest, it also acts only over very, very small distances, less than the size of an average atom. But gravity, on the other end of this list, acts over the largest universal distances, just ignore that, universal distances, while also being the weakest. If you might remember from physical science, an example I have of this, I got my avocado here. On the back of my avocado is a magnet. And if I have it a little ways away, electromagnetism is stronger than gravity, right? You can tell how. Okay, so yeah, if I do that with something that's not magnetic, that just keeps falling. But electromagnetism at that scale is stronger. I'm stuck. But if I pull even a little ways out from the board, gravity is stronger because it's a matter not only of strength but of range. Here's an applicable analogy for you. If you're a runner or a track star, if you're going to run away when it gets hard, an analogy for you is that sometimes you can run very fast, but only over short distances, and sometimes you can run a long ways. But you got to kind of, what would Eric Smiley tell you? You have to kind of pace. Yeah, exactly. Imagine you saying that tight. Okay. So we've got the universe here, and it's made of these things. And the question from lesson 1 is, the big question, the 15-cent question is, how, what's the rest, do you think, going to be in science?
How does it
do we know? How do we know? How do we know what that's like? How do we know it's not, like the ancient Egyptians thought, a very, very dark woman arching her body like this over top of planet Earth with stars on her front? How do we know it's not like the ancient Israelites thought, where it's the lapis lazuli floor of heaven that we're seeing into?
Because of this.
And also, in a sense, is it kind of like that on some other level? Maybe. But you're exactly right. We use observations. How do we know? We observe with our little eyes. Yeah, sure. Sometimes. But that's what the ancient people were using too. But we also use tools. And those tools are, especially, we talk about, I'm going to list these things for you. Ready? And you're going to list them too in your notes. Parallax. Parallax. The electromagnetic spectrum. I'm going to spell it really wrong and with terrible handwriting. Let me start over.
Parallax is the little dragon from Skyrim.
I don't think that's true. I don't know enough about Skyrim to know whether that's true or not, but I don't think that's true. Electromagnetic spectrum. And I think we're going to include in this, I can't remember if your book uses this word, and I'm trying to look up if it does or not, but I'll just tell you anyway, and then you can, whatever your book says, we'll sort that out later. HR diagram. Those are going to be the main ones that we look at, and they're related, of course, as all things are, but these are specifically related. This one I think is really easy. I'm going to draw a diagram of this after we do it, but that also reminds me of the objective, which I want to tell you now because it directly relates to these things. Would you please? I can't see it with the glare. Emma, would you read me the objective aloud?
Analyze and interpret data about the structure and origin of the universe.
Good. Analyze and interpret. Emma chooses to say data. I almost always say data. They are the same word, but you should that word is plural. I don't know if you knew that, but that word is plural. If I have more than one, they are data. If I have only one, it's a datum. Anyway, analyze and interpret data, more than one of them, about the structure and function, and origin, sorry, I'm used to saying structure and function from the CCC, origin of the universe. Well, guess what? We already defined universe, but now we're talking about specifically, we're talking about the data. How do we get that data? Emma would say data. How do we get that data? It's mainly, there are more. This list is also non-exhaustive, but the ones your book goes into most detail about are these. The first one has to do with how far away. How far away. If this were a vault of stars, as in either of those ancient examples that I gave earlier, the Egyptian or the ancient Hebrew, if it were a vault of stars, we would expect to see them as they appear to us with our naked eye, as pinpoints of light. But because of this phenomenon of parallax, we can learn how far away they are. And to demonstrate parallax, I want you to find something in your field of vision and hold your thumb up and close an eye. I'm going to use the flag, but you're not because you're facing the other direction. Dalton and I can use the flag. So close one eye and hold your thumb up and cover up or partially cover something, and then just switch eyes. It's like magic. It's the magic of science. So using the power of the magic of science, you can move an entire flagpole that is more than 200 feet away from you. You can't, but your perception is that you can, right? Do you see? That's called parallax. Thanks, Gunnar. So you might have been covering up part of my face, as you also might want to, just because of the way I grade your assignments sometimes. But you're covering up part of my face, and you can move my whole body with just closing and opening your eyes. The way we do this is that in its orbit around the sun, here's the sun, Mr. Golden Sun. I'm not going to draw a smiley face on him. I don't think he's happy. And in Earth's elliptical orbit, if we're here, we being me and you and all the other humans, are here in June and here in December, the stars will look slightly different. So here's a star, there's a star, and if we see, I tried to pretend I got it right. It's the same kind of thing. Does that kind of make sense? So instead of, we don't get to close one of Earth's eyes or use a telescope with binoculars because that's not far enough away. But by knowing this distance and knowing how much they change this angle, we can get the side angle side postulate of triangles, and we can find this hypotenuse. And guess what that tells us? What's this hypotenuse?
Parallax.
Oops. How far away? This hypotenuse of that triangle is how far away. I don't expect you to know the math, but if you've been in pre-calc or trigonometry, you know that this is not that hard because you can do this math with a triangle. So with this fairly simple tool, we can learn how far away the stars are. And guess what? They're not 10 miles away above us. Not in a real observable way. In a physical observable way, they're not. I'm not trying to throw shade on the ancient Egyptians or the ancient Hebrews, by the way. Those things could also be true poetically or metaphorically. That's fine. But observably, physical reality is that these things are light years away. That's one of your vocab words that I expect you to know. These are light years away. That light would take several years to reach them. So that's the power of parallax. The electromagnetic spectrum, does that what I told you about parallax timing make sense? Can you relate this to what you did with your thumb? Does that, I'm getting a vibe of what's going on right now. But does this kind of make sense to you?
Yes.
Okay, I'll buy it. Okay, the electromagnetic spectrum. Justice, remind me, what is the electromagnetic spectrum? Could you say it in a song, perhaps? No, red, orange, yellow. Hold on, I'm trying to do this. I like to do this because it makes it beautiful. Yellow, green, blue, purple. Purple in the Rainbow Light Show. This is from, I don't have a purple, just give me a break. Just give me one break, okay? I could have just wrote them out, but instead I try to do it this cute way. Red, orange, yellow, green, blue, purple. And that's because this comes from a song that I learned from one of Asher's toys that tells you the colors of the rainbow, and it does it with that way. This is the electromagnetic spectrum. Is this the whole electromagnetic spectrum? No. Let's go down. What's below red? Someone might even say infrared. Infrared is here. Infrared. What's below infrared? Do you know?
Microwave.
Yeah, great job. I'm not amazed, but I'm impressed you knew that. And then what's below that? Radio. Oh, hey, but check it out. Ultraviolet might even be, if infrared is infra, below red, what might ultraviolet be?
Ultra-red.
It might be above violet. Ultraviolet. And then what's above that?
Ultraviolet.
X-ray. And then above that is gamma.
Gamma ray.
And actually, it kind of, this in not so much, radio trails off into infinity, approaching in infinitely long wavelength and infinitely low energy. And gamma trails off into infinity. It's an asymptote approaching infinitely high energy, which obviously you know can't happen. It becomes a Kugelblitz, which is a type of black hole. It approaches infinitely high energy and infinitely short wavelength. And because of that, that's how we can remember that this direction is increasing. Oh, don't write right over the top of it, you silly guy. Increasing wavelength goes this way. I'm doing this fast because what's going to be my excuse? Can you guess?
Time.
No. Well, okay, sure. That's actually the reason. But what's the excuse?
I'm not ready.
You knew it. You knew this in 8th grade. You took tests over this. Increasing wavelength is that way. Increasing energy is to the right. Like that Beyonce song about to the left. What?
So when we send signal that to space, is that all radio?
Yeah, that's what I'm getting at here. The reason I had written in green, it was up here, but in electromagnetic spectrum, is that when we look through a telescope in with our naked eyes, well, it's with a telescope, we see visible light. Like, what's her bucket's Stanley Mug being pink, or Kessen's, the other girl, I can't remember anyone's name, red shirt, see? That's visible light that we're seeing reflected. You'll notice in my diagram, I drew these not at all. We can't see them at all. I just put them in brackets. You can't see them, but we do by using things like radio telescopes or X-ray telescopes or infrared telescopes. We can see things that we wouldn't see with the visible spectrum. So that's a tool to gather data about the observable universe that we wouldn't have otherwise had. And we do that with machines, basically.
I have one more question.
Let's hear it.
So when they scan the ocean floor, what kind of waves?
Usually that's sound waves, to my knowledge. I'm sure there are other ways, maybe even better ways, but to my knowledge, the ocean floor is discovered with sound waves.
Those are really slow.
And sound waves are a whole different thing. They're a physical medium. They're the vibration of atoms, where this is the height and energy and frequency of the electromagnetic radiation itself. What was the other thing that was on my list? I can't even remember now. HR diagram. Okay, and this is going to be our last thing. HR diagram. Your book doesn't use this exact term, but that stands for a German person's name, Hertzsprung hyphen Russell. These are two people's names. Hertzsprung-Russell diagram. I think your book does give a kind of example of it on page 259. If you look, is that showing up? I want the diagram.
Where?
What do you mean where? The diagram with like the stars and stuff. Listen. Oh no, all my papers.
Yeah.
There you go.
Got it? Okay, you can pause it if you're watching this on YouTube later. So that diagram, using the colors and distance of stars, we can tell what that star is like. Thank you so much. I didn't mean for you to have to do that. And let me tell it to you this way. We've got, on the Hertzsprung-Russell diagram, instead of erasing something, I'm just going to do this whole little section over here, okay? The temperature of the star is on this scale. This is not going to turn out very well, I don't think, but I'm sorry, what did you say? This is the color diagram of stars, and if you had to guess, I'm doing this on purpose. I don't want you just to be wrong, but I am doing this on purpose. If you had to guess which end of this, left or right, is going to be the hottest stars. Left is the correct answer. So these are the hottest stars, and these are the coolest stars. Red is cool, and we have this kind of flipped in our cultural imagination because to us, fire, hot, red. But in reality, if a really hot fire is actually, if you've seen the lab Bunsen burners or a welding flame
Or
or
a talkie.
a talkie, yeah, yes, thank God for talkies turning the paradigm, the cultural paradigm around. We got blue to be hot, which is how it is in reality. The hotter a thing gets, the bluer it gets. And so, depending on how we see the color of stars when we look through a visible light telescope, it tells us their temperature. And then using their temperature in combination with how far away they are, which we learned about from parallax, we can also learn their size. And we end up with several classes of stars. We have what are called main sequence, which will bring us to our last point. Main sequence stars. We have dwarfs. To my knowledge, it's always FS. It's never VES. Dwarfs, giants, supergiants, and hypergiants. And I should have listed these in a different order now. The dwarves in the main sequence, if you haven't written it yet, you should switch those. Main sequence are larger than dwarfs. And so they can be a combination of a color and then one of these sizes. And how do we know the size if they all just show up as pinpoints in the sky? Carson, sit up. How do we know the size if they all just show up as pinpoints in the sky? Telescopes, and how far away they are. So we see their size from Earth called apparent magnitude, and we know how far away they are using parallax. And so then we can say, well, it seems to be this big, but we know it's this far away, and so it's actually this big. And I don't expect you to know that math, just that it exists. And then so we know their size and their temperature, and between those we get the Hertzsprung-Russell diagram, which I showed you on the camera. You're so welcome, Gunnar. And the reason that there is this difference at all is because what makes a star? That's what we're going to talk about last. What makes a star? I'm going to erase all of this, and I'm just going to call this stars. And actually, the first YouTube video I ever made in my entire life was an explanation of how stars are formed. And it's not just burning. What are the two forces acting, do you think? Gravity, pulling.
Gas.
Okay, but pulling which direction? In. Okay, so we start out with a cloud. This is going to be the origin part from our objective. We start out with generally a cloud of gas and dust, like we talked about in the previous unit. And that cloud of gas and dust, by its mutual and consolidated gravity, pulls in, and eventually, at some point, it gets so tightly packed because of, again, gravity, our good friend, because of gravity, that the strong nuclear force starts nuclear fusion. So instead of a hydrogen atom and a hydrogen atom just flying around, like it is in a gas in Earth's atmosphere, for instance, gravity smooshes them together, and they start to fuse, nuclear fusion. So stellar fusion occurs. And then that stellar fusion has an outward, pressure is the word we actually use. It's not the same as mechanical pressure, if you remember from physics or physical science, Gunnar, put that away. But it's an outward pressure. It causes an outward force. Stellar fusion forces the star outward. And so in a main sequence star, which I'm going to draw in yellow, even though our sun is white, we often call it a yellow main sequence star, which won't show up on the camera. I'm now becoming aware as I'm currently drawing it. Is it showing up at all on there?
Yeah.
Okay. I'm going to do the rest in black. So there's a balance of forces. The inward force of gravity, I'm going to label that in black. Gravity. The inward force of gravity, which is black, balanced with the outward force of stellar fusion, causes the shape of this star. You might think this is a sphere, and this is a sphere because of the way it is, for lack of a better, I mean, really that's it. It's the shape of a sphere because it's the shape of a sphere. Like that's the way this object was manufactured. A star is not the shape of a sphere because it's one single object. It's still basically a gas cloud, a plasma cloud. It's the shape of a sphere because that is the shape that best balances the outward force of fusion with the inward force of gravity. It's actually the shape of a sphere because a bubble is the shape of a sphere. In a bubble, the outward air pressure is balanced with the surface tension and the inward air pressure to make it a circle. Bubbles are always circles, SpongeBob. At SpongeBob SquarePants, bubbles are actually always circles. They're spheres, I mean. And it's the same reason that stars are spheres. This is how a star forms. Lots of gas, consolidated by gravity, forces stellar fusion to occur, and that balances with the gravity that's still acting on it to form a single star. Stars, in a way, back to what we had at the beginning, stars and the measurement of stars using these methods tell us not just about them and galaxies, which are a group of stars, but they tell us that really stars are a function of space itself. If you have space and there's stuff in it, eventually, because gravity is universal, eventually stars will form. Neil deGrasse Tyson tells you, Carl Sagan also tells you, that you are star stuff. The stuff that you are made out of came from a star, and I think that's beautiful. You are yourself a little star. Do you have questions?
I love Neil deGrasse Tyson. He says that the Earth is a cube all size.
This doesn't sound like a question.
I have a question.
Yes, Hunter.
So, like, flat Earth, do I love you? There's no way that could.
It is observably false,
Yeah.
demonstrably false, right? Like you can demonstrate that that's not true. But it's based on people's beliefs.
Yeah.
And who can change another person's beliefs, really? I mean, you can show them the evidence, but unless you take them up in a rocket ship and say, it's a sphere, look at it go, which they probably would even refute at that point, you can't change people's beliefs. But luckily, people's beliefs don't change the world either. So you just, at some point, you just got to let people believe what they want. And that's totally fine. Everyone has beliefs. No one can observe all of reality and therefore have all of the evidence that they need to be right all the time. And so at some point, everyone is believing. Bye.
Do I